So we've been looking at how we can use a little bit of calculus to be able to determine a lot of different things based upon amount of time that's passed, whether or not we've got our starting or final concentrations, and what the overall rate order of our reaction is. But there's a piece that's missing. You may have noticed that oftentimes we're told at 25 degrees because we know that temperature affects the rate of a reaction. If our temperature has increased, we would expect our particles to collide more often. As a result, we would see an increase in our rate of the reaction. Now, that's not going to be affected by the concentrations. There's really only one piece of our rate law that could change then, and that is our rate constant. K is temperature dependent. And so we got to talk a little bit about Arrhenius and what happens if we change the temperature of our reaction. So for our Arrhenius equation, we need to be looking at the effect temperature has on our rate and via our rate constant. So here we've actually got temperature versus K. And so over the course of time, as we increase the temperature, we see an increase in our rate constant K. So Arrhenius originally came up with this idea that we could solve for the K using what's known as the activation energy and our particle collisions factor, our collision factor, frequency factor, that's our A value here. E being our second function of our natural log, R is the universal gas constant, T for temperature. A lot of kind of variables here when you think about particles and their physical collisions and all this stuff kind of coming together. That being said, I'm not going to do the full derivation here. If you're interested, I know there's a lot of videos out there for it. But what we can actually do is if we have K at one temperature, K at another temperature, not unlike what we did with the rate laws where we took one and we divided by the other to get rid of some of our constants, we can actually rearrange this a little bit and solve then for our modified Arrhenius. And so here is our modified Arrhenius equation. It's kind of a little cumbersome, but what this allows us to do, and this is kind of our dual credit piece, it lets us, if we know our original rate constant, so K1 would be the original rate constant, at its original temperature, T1, we could then solve for either a new rate constant if we needed to, or we could solve for an activation energy if we knew what our new temperature and rate constant were. And so EA here is just activation energy. By definition, that is the minimum energy needed to have a successful collision to create our products to form. R is our energy gas constant. T is just our temperature in Kelvin. Watch out for that. It does have to be in Kelvin, plus 273.15. We're going to add that 0.15 on there. 273.15 plus our Celsius to get into Kelvin. And A is our collision of frequency factor. Now, the good news is for a reaction, that A is going to be constant. So it ends up dropping out, which is nice. Letting us have kind of this modified radius. It is not on your equation sheet, but I will provide that for you. I'm not expecting you guys to memorize this one. We just don't have the time and energy necessary to be able to do that this year. So cool. EA, again, is the minimum energy that our particles have to have in order for a reaction to occur. So let's take a look at one of these. Oh, there's that decomposition hydrogen iodide. We know that its rate constant is very, very slow. It took a really long time for this reaction to occur, but it does go faster if we increase it by 100 degrees or 100 Kelvin. And given this information, given the two constants, given the two temperatures, we can actually find the activation energy, the minimum energy needed for this reaction to go, which is kind of slick. So we're going to use our formula. We're going to use our formula and we're going to plug in everything that we know. Here's our kind of modified Arrhenius. We know K2, that's going to be our bigger temperature, right? Our larger number, 1.1 is our K2. Our K1 was the 9.51 e to the negative 9th, excuse me. And we know R, we're going to use the gas constant, but we need the one with the right units. Otherwise, this isn't going to work. It looks like we've got some Kelvin coming off of our temperatures. I think we're going to want energy, so we're going to want our R that's got joules. Our joules is the one we're after, so it's that 8.314. This is available on your equation sheet. Here we went ahead and just rearranged. If we're going to solve for EA, we would need to divide it. Oh, sorry, we're multiplying up the negative R to the left-hand side, and we've actually got the reciprocal to the negative first of our temperatures. We can plug in everything, and this lets us solve all in one go. If it makes more sense to plug in the numbers that you know, condense it to one value, and then divide it over, that is totally fine. Whatever makes more sense to you. But we can plug in all our values and solve directly for that EA. In this case, it'd be 1.76 times 10 to the 5th joules per mole or be 176 kilojoules, just watching out on those units there. Cool. Just want to introduce this formula to you. We're going to practice this when you guys come back and debrief and make sure we're doing okay. But I just want to introduce it, have you get these notes that you've got them. We're going to be kind of moving forward from here into the next piece of our unit.